Hello everyone, today we are going to discuss the master method. The master method is frequently used to solve recurrence relations, so it is important for analysis of computer algorithms. Let's start. There are three common techniques for such complexity analysis: substitution method, iteration method, and the master method. In this video, we will use the iteration method to derive the master method. So let us summarize the iteration method again. In the iteration method, first we expand the recurrence, then do some algebra to express it as a summation, and finally we evaluate the summation to get the complexity of the algorithm. In this lecture, we will solve a generic recurrence relation using the iteration method, and finally we will see that it gives us a format which is called master method for complexity analysis. So let's consider this generic recurrence relation. When n equals 1, then the cost is c, and when n is greater than 1, then tn is atn by b plus cn. As we are applying iteration method, first we will expand the recurrence. So we will expand this term. So Tn equals Atn by b plus Cn as given here, and when we expand the term Tn by b, then we get Tn by b equals Atn by b plus Cn by b. After simplification, we get a square Tn by b square plus Cn a by b plus 1. Following iteration method, now we have to expand this term. So after expansion, we get this representation. Then after little bit simplification, we get a to the power 3 tn by b to the power 3 plus cn a square by b square plus a by b plus 1. So here we can see that at first it was a to the power 1. Then after the second expansion, it was a to the power 2, and after the third expansion, it is a to the power 3. So after the kth expansion, it will be a to the power k, and similarly we can write the kth expansion as atn by bk plus cn ak minus 1 by bk minus 1 up to 1. So according to the iteration method, we have completed the expansion of the recurrence relation. Now we will represent the series as a summation. So we know that the value of t1 equals c. So if we put n equals bk, for the sake of the discussion, let us denote it as equation number 1. So if we put n equals bk, then equation number 1 can be represented like this. And we can put t1 equals c. So the simplified version is this one. So we can reconsider the common term c. So a more simplified version can be written like this. And for further simplification, we can write it as Cn ak by bk, and we know that n equals bk, and finally we can write it like this. So now this is the expanded and simplified version of this recurrence relation. So now we will evaluate this series to get the complexity analysis of the corresponding algorithm. So we know that this is the simplified version of formula 1. And for this series, we can consider three different scenarios: a equals b, a less than b, and a greater than b. At first, we will consider the first scenario. So if a equals b, then we get a total of k terms here plus 1. So we can write formula 1 as Tn equals Cn k plus 1. And we know that k equals log n. So we can write it as Cn log n plus 1. And from here we can write that the complexity of this term is n log n. So it is big theta n log n. Now let us consider the second scenario where a is less than b. So when a and b are not equal, then we can summarize this series with this formula. So according to this formula, the series in equation 1 can be replaced with this term, and we can see that this term is less than 1 by 1 minus a by b, and this term is constant. So we can write Tn equals Cn big theta of 1. So finally the complexity will be big theta of n. Now let us look at the third scenario where a is greater than b. So when a is greater than b, we replace this series with the previous formula. So we can replace this series with this term. So since a is greater than b, then we can say that the complexity will be dependent on this term. So we write the complexity as big theta of a by b to the power k. And we know that k equals log n, so we can further simplify this term. And after some simplification, we see that the complexity is big theta of n log a. So we have seen that this recurrence relation can be simplified to formula 1, and then we considered three different cases: a equals b, a less than b, and a is greater than b. And based on these three considerations, we get three different complexities. So when a is less than b, then the complexity is big theta n. When a is equals b, then the complexity is big theta n log bn. And when a is greater than b, then the complexity is big theta n to the power log ba. We can use this format to solve recurrences of this format, and this is called the Master Theorem. So for a divide conquer algorithm, if the main problem size is n and the divide conquer algorithm divides the main problem into a number of subproblems, where each subproblem has size n by b, and the cost for divide operations as well as the conquer operations at each stage is defined by the function fn, then we can apply the Master Theorem to find the complexity of the recurrences. This is a generalized representation of the Master Theorem. The recurrence is represented as Atn by b plus fn, and the cost of t1 is c, and the complexity of divide and conquer operation at every stage is polynomial. Then we apply Master Theorem to find the complexities. So let us solve some examples. So let us consider this recurrence relation, and this is our Master Theorem. To apply Master Theorem, we need to know the value of a, b, and d. Considering this equation, we see that a equals 1, b equals 2, and d equals 2, considering this term. So the complexity can be found comparing a and b to the power d. So a equals 1 and b to the power d equals 4. So we see that a is less than b to the power d. So the complexity is big theta n to the power d. So the complexity of our algorithm will be big theta n to the power 2. So the complexity is big theta n square. So it's very easy. Let us consider another example. Here we see that a equals 2, b equals 4 and d equals half. So let us compare a and b to the power d. So a is 2 and b to the power d represents 2. So we see that a equals b to the power d. So this case will be applied. So the complexity will be big theta n to the power half log n. So it will be root n log n. But there are some restrictions to apply the Master Theorem. We cannot apply Master Theorem if Tn is not a monotonic function. And we already said that Fn needs to be a polynomial and B should be a constant to use the Master Theorem. So it's very simple. We can use Master Theorem to find the complexities from recurrence relations. Thank you all.